Welcome to Study Loop.
Hi. So in this problem, it is given that it is given that if there's a cable between 2 points A and B, cable hanging between these two supports A and B, this is the cable, and C is its lowest point, and XY coordinates like we take from the lowest point. So these are the XY coordinates, and from any point on this coordinate, it it makes some angle with the cable. Let a point be D between these 2 points, and so this angle would be, let's say it is theta. So it is asked in this question that if the weight per unit length of the cable is given to be W naught over cos square theta, it is asked that prove that this cable makes a circular arc, that this AB, prove that AB is a circular arc, that is an arc of a circle. We have to prove that AB is a circular arc. Okay, so in this question we will use a property that we derived in the previous question, namely in question 124 we derived a property that if Wx is the weight acting on the cable, Wx is the a distributed load acting on a cable where x is this coordinate and y this coordinate, then x and y for the cable are related as, and the equation of the cable is double derivative of y with respect to x is equal to Wx over T naught, where T naught is the horizontal tension in the cable, that is tension at the lowest point. Okay, so using this property we will prove our question. Okay, now let's start it. So prove this, we will take an element of the cable. Let this be one small, wait, let me draw it again. So let's take a segment of the cable. So this is a little segment of the cable, that is ds is its length and dx is the horizontal distance of this segment, horizontal, and this angle is theta. This angle will be the same as the angle made by from the coordinates for this arc. Like this angle would be also theta, so this will also be theta. Okay, and from this element we can see that this dx is the projection of the cable onto the horizontal axis. So dx is cos theta times ds. Okay, okay, and as we know that the weight per unit length of the cable is given by W naught over cos square theta, we can say that for this length ds of the cable, this would be the complete weight of the cable, and this would also be equal to the weight per unit this x coordinate times dx. Do you understand this equation? So these two are similar quantities, the complete weight of the cable. Okay. Okay. Now let's substitute this equation into this. Let's substitute ds equal to d. So from here the ds is equal to nothing but dx over cos theta. Substituting this into this equation, we get wx dx is equal to w naught over cos square theta, and ds is dx over cos theta. So dx is cancelled. So this becomes wx equal to w naught over cos cube theta. Okay. Now let's apply the equation that we had proved in the previous question. That is, let's apply this equation. So according to that equation, d square y d square, let me rub this and write it again. So from the double derivative of y with respect to x is wx over t naught. Let's put this. So let's put the value of wx into this equation. So it becomes d square y over dx square is equal to w naught by t naught over cos cube theta. Okay. Yes. So we will call this equation as equation number 1. Okay. And now we'll get another equation. So the other equation is, we know that double derivative is nothing but the derivative of the single derivative. So d square y1 dx square should be equal to derivative of dy over dx. And if this is the cable, then rate of change of the height y with respect to x would be equal to the tangent of the angle of the cable. That is either this angle theta or this. So we can write dy upon dx as tan theta. So this becomes du by dx of tangent of theta. And this can be written as, do the derivative of tangent theta is secant square theta d theta over dx. Okay. So let's write the LHS here, left hand side. So this becomes our second equation. So let's use these two equations. Let's substitute the value of the left hand side, that is this, the right hand side of this, and put it in place of d square y over dx square in the second equation. Okay. So from here we get w naught over t naught cos cube theta is equal to secant square theta into d theta over dx. Okay. So from here we can write d theta over dx as w naught over t naught cos cube theta and secant square theta. As you know that cos and secant are inverse of each other, so this becomes d theta over dx is equal to w naught by t naught cos theta. Okay, so from here dx can be written as to be equal to t naught over w naught dx goes here, and d naught cos theta d theta t naught by w naught cos theta and d theta. Okay, so if we substitute t naught by w naught as equal to r, because this is a constant, and we will later see that this will become the radius of the circle, then then dx becomes equal to r cos theta d theta. Okay, so our dx equal to r cos theta. So this is the equation of the circle with the radius as r, and with red, not the complete equation of the circle, but this will prove that our arc is a circular arc. If it subtends angle theta from the center, if this radius is r, then rate of change of this x will depend on change in theta in this way. And we can also prove that, see, if the rate of change of x from theta here comes equal to r cos theta, so we can see that this x will change according to the cos of this angle. So at this point, when the theta would be 90 degree from the origin, so from this point, if this would be 90 degrees, if this will be 90, so cos of 90 is 0. So, and we can also intuitively see that after this point, the change in x will be negative. The x will start decreasing. So that satisfies our intuition. And so we have proved that this is this if the we have proved that if the weight per unit length is w naught over cos square theta, then the equation is of a circle. Then it makes a circular arc. Thank you very much for following.